Our first example, we want to graph this function, label the vertex, axis of symmetry, and any intercepts. Okay, so we've done vertex and axis of symmetry before, but that was when it was in a certain form. See, this function is in the standard form, so we have to complete the square to get it into the vertex form, which is f of x equals a times x minus h squared plus k. So it's going to be a little more difficult because this is not an equation. We are trying to complete the square with an expression. And that means we cannot do whatever we want. We can only multiply by 1 or add 0. And add 0 is what we're going to do, and I'll show you how. So I'm going to associate just the variable terms. The minus 5 I'm going to just push over to the side. It's still on the same side, but I'm going to push it over a little. So I want to complete the square. So I need to add half of b squared here. So half of negative 4 is negative 2, and negative 2 squared is 4. So I'm going to add 4 to this expression, but I can only add 0. So if I'm going to add 4, I have to subtract 4 in order to be adding 0 to the expression. See what I mean? And the reason why I added 4 was to complete that perfect square trinomial so that that factors to x plus half of b. Half of negative 4 is minus 2. And then on the outside, negative 5 minus 4, I can add those together. That's negative 9. So this gets me the vertex form so that I can identify the vertex as the 2, because it's the opposite of negative 2, so that's positive 2. And negative 9 for y. So that's the vertex, 2, negative 9 right there. Now I need axis of symmetry and intercepts. So I'm going to go for the intercepts first. I guess it doesn't matter. Let's do the axis of symmetry. That goes through the vertex as a vertical dashed line, so x equals, in this case, 2 for the axis of symmetry. But I don't have any other points yet, so let's get some points here. Intercepts. Let's look at the y-intercept first. Find the y-intercept, we set x equal to 0. So 0 for x, 0 for x, and let's see what happens with y. That's 0 plus 0 minus 5, so negative 5. That makes the y-intercept 0 for x, negative 5 for y. So 0 minus 5 is right there. That's the y-intercept. Now I need some x-intercepts. That's where y is 0. So instead of f of x, I'll put 0. And I use the standard form for the y-intercept, but it's easier to use the vertex form for the x-intercept. And the reason why is because, look at this. This is a square and a number. If I move that number over to the other side of the equation, then 9 equals x minus 2 squared. And I can go ahead and use the square root property, right? So that plus and minus 3 equals the radicand, which is x minus 2. And then I just need to add 2 to both sides of this equation, so that x is 2 plus or minus 3. So that gets me 2 x-intercepts, right, where y is 0. 2 plus 3, that's 5. 2 minus 3, that's negative 1. So those are the x-intercepts. 5, 0, and negative 1, 0. That looks good. So if we were to go ahead and connect those together to show this parabola, that's what that would look like. There's a question here, though. Can you identify another point using symmetry, using that axis of symmetry? Because you can tell that each of these points, each of the x-intercepts are symmetrical over the axis of symmetry, right? So then these points would also be symmetrical. This would have to be in the same spot. If this is 2 units to the left, this is 2 units to the right. And so that point would be 4, negative 5. So 4, negative 5 is another point by symmetry. There's a helpful hint here about your x-intercepts, because the example that we just did had 2 x-intercepts, and that's because the discriminant of that quadratic function was positive. We didn't find the discriminant, but it is. So there are situations where you don't have any x-intercepts, right? That's a possibility. And we can tell because the vertex is in either the first or the second quadrant and it opens up. In that case, there's no x-intercepts. Or if the vertex is in the third or fourth quadrant and it opens down, then there will be no x-intercepts. So it depends on where the vertex is and whether it opens up or down. How do you know whether it opens up or down? Up is a positive a times x squared. Down is a negative a times x squared. So if that coefficient of the x squared term is positive, opens up, negative opens down. So that's how we can determine whether we have any x-intercepts at all, and that's important. If there aren't any, why bother them? So another example here, we have a function. It's in the standard form. We need the vertex, axis of symmetry, and intercept. So again, we need to complete the square. So what we're going to do is we're going to just associate the 2x squared plus 2x. Push the plus 5 away. Still on the same side, but push it over. And so I can't complete the square here because there is a coefficient of the x squared term. I'm not going to divide because remember, I can't. If you have an expression, you can only add 0, like I said, or multiply by 1. So I can't do that. But what I could do is I could factor out. I could factor out the 2 and then divide 2, because that's multiplying by 1, right? 2 over 2 is 1. So let me do that. And just for those terms, it has nothing to do with this plus 5. He's pushed over to the side there. He's not part of this association. So now I can complete the square. Half of 1 is 1/2. So 1/2 squared is 1/4. But am I adding 1/4? I'm actually adding 2 times 1/4. So be careful. I'm adding 1/2, essentially. So I need to subtract 1/2. So I completed that square, x plus half of 1 quantity squared. And then outside I have 5 minus 1/2. So I need to get a common denominator here of 2. So that will be 10/2, same as 5, minus 1/2. And that gives me positive 9/2 altogether. That's not fun. Okay, let me put those in decimals for the vertex then. So the opposite of 1/2, that's going to be a negative half, which is 0.5. And a positive 9/2, the 2 goes in 4 times with 1/2 left over. So 4.5. That's our vertex. Negative half and 4.5. So right there's our vertex. Okay. Then axis of symmetry goes through that vertex. It's a vertical line, dotted line. So x equals negative 1/2. Now we need some points. So let's go for some intercepts. The y-intercept is easy to find in the standard form by evaluating that at 0. So 0 for x in the original function, because that's 0 plus 0 plus 5 is 5. So when x is 0, we get 5. That's right there. Y-intercept. Now we need x-intercept, which is easier to find by the vertex form. But remember that helpful hint. We have a vertex in the second quadrant. And does this open up or down? It's positive, so this opens up. So that means we're not going to have any x-intercepts, right? There's no x-intercepts. So we need some more points here. Let's just evaluate the function at another value. Let's say negative 2. See how that works out. So 2 times negative 2 squared plus 2 times negative 2 plus 5. So that's 4, and 2 times 4 is 8. Minus 4 is 4, plus 5 is 9. Okay, so negative 2 for x, 9 for y. Gets us a point there. And by symmetry, that's 1.5 to the left of the vertex, so 1.5 to the right is another point by symmetry. And that looks good. We can connect those together to finish the graph of this parabola. Finally, we want to graph this function, find the vertex axis of symmetry and any intercept. So again, we need to complete the square here. I'm going to associate the variable terms. Kick to the side the 8, the constant. Now this needs to be positive 1. So we need to factor out a negative from just these two terms. So negative will give us a positive x squared and a positive 2x. All right, now we can complete that square. So half of 2 is 1, and 1 squared is 1. But I'm not adding 1. I'm adding negative 1. So if I add negative 1, I have to add positive 1 so that I'm actually adding 0. I'm not changing the value of this expression. Okay. So that completes the square. So this will be x plus half of 2, which is 1, quantity squared. On the outside, those add together, 8 plus 1 is 9. So this gets us our vertex, which is the opposite of this. So negative 1 and 9 for y. That'll get us a vertex right here. And hopefully it opens down, because otherwise this is going to go off of our graph, right? So the axis of symmetry goes through that vertex. And that is x equals negative 1. All right, now we need some intercepts. Let's go y-intercept where x is 0. So I'll evaluate that in the original function. Just easier that way, because that's 0, and 0 plus 8 is 8. So 0, 8 is our y-intercept. So right there. So I can see this does open down, and I can tell because of this. Opens down if the coefficient is negative. So that means we do have two x-intercepts here. So let's find them. X-intercept is where y is 0. So I'm going to put 0 in for y, or g of x. And I'm going to use the vertex form just because it's easier to solve it this way. Because I just want to subtract 9 from both sides, so that negative 9 equals negative x plus 1 squared. Then I need to divide that negative to isolate the square on the right side. So 9 is x plus 1 squared. Now I can use the square root property. So that'll be plus or minus 3 equals the radicand. And then just subtract 1 from both sides. So we'll have two x-intercepts here. The first one is negative 1 plus 3. That's 2. And the second one is negative 1 minus 3. That's minus 4. So 2, oops, wrong place. 2, 0, and negative 4, 0. Okay. Looks good. We could also do another point by symmetry if we wanted. Connect those together to finish the graph of this parabola.